So in honor of the release of the new Star Trek movie, I'm going to show you the WFirst trailer to start with. And the link's on the first page. All right, where did my talk go? There we go. All right. So the good news is that even though that movie showed WFirst being in low Earth orbit, apparently it's a very scary thing. It will in fact be in L2, far safely away, doing some really excellent exoplanet science. You already heard, of course, about the microlensing this morning. Here is the sort of cadre of science programs currently scheduled for WFirst. So this is sort of a bucket of wide field surveys to attack these various different questions. We have the microlensing census that, of course, will give us great statistics on exoplanets. Coronagraphy, which I'm going to talk about today, but I also want to highlight this box over here. So 25% of the WFirst time will include a guest observer program. So even though this is a survey instrument and there will be a coronagraphic survey component, there is potential for you folks to actually use the coronagraph on WFirst to do science. All right, forward here. So here's a little picture of the WFirst Observatory. Am I missing? That's weird. Okay. For some reason, some of my titles didn't come through. We'll be okay. So here's the wide field instrument. So here's all your mini 300 megapixels worth of imaging. And then the coronagraphic instrument is sort of tucked in down here. And you've, of course, heard about the AFTA, our special delivery from the black side of the government. And what I'm going to do now is I'm going to play another little movie. So although I do have an engineering background, I'm a theorist by training. So most of what I know about is the excellent sort of atmospheric science we're going to do with WFirst. So I'm going to let Nick Siegler tell you about the basics of how an internal coronagraph works, and then we'll get into more of the details of exactly how the WFirst coronagraph works.
A distant star is orbited by two planets. One looks similar to the Earth, the other is a gas giant. When viewed from a distance, the two planets disappear into the glare of their sun. How could we ever find these planets all the way from the Earth? By using a space telescope with a coronagraph to separate starlight from planet light. As the star's light passes through the telescope's large mirrors, it picks up small distortions. Diffraction adds concentric rings to the image we see. To reveal the planets, first a coronagraph uses a mask to block much of the star's light and redirect the remaining light to the outer edges. A washer-shaped device can now block most of the rest of the star's light. Because the planet's light comes in at an angle, it misses the mask and passes through the center of the washer. But when we turn up the image signal by collecting more light, we can see that the planets are still hidden under blobs of leftover starlight. To remove these blobs, the Coronagraph has a special deformable mirror that can change shape by using hundreds of tiny pistons. This can correct distortions in the light beam. As the mirror deforms, the blobs of light as seen in the monitor slowly begin disappearing, finally revealing the brighter of the two planets. Afterwards, the fainter planet also comes into view. We can now see objects more than 1 billion times fainter than the star. And if the light from these planets is passed through a prism, we can spread it out into rainbows of color. But some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
I really encourage you, if you give public talks, to go check out all of these great movies that explain the basics. And I show this, many of you may be experts and know all this, but I know there are a lot of different varying levels of understanding. And so hopefully that gives you a basic idea of how an internal coronagraph works. Now this of course has been done on the ground with facilities such like GPI, but WFirst will be the first space-based one, okay? So here's what it looks like. This is of course just a little diagram of what's going on. And I thank Charlie Knocker for these slides here. So, darn it, back, forward. We don't want to watch the movie again. There we go. Sorry about that. You should know that the WFirst coronagraph is being designed and built and tested here at JPL. And here's a basic layout of what's going on. You have all of these different optical paths. We want to highlight, of course, this speckle control via deformable mirrors up here. This supposed to be brown line, looks a little purplish. But also in the red lines, you see this low order wavefront sensor. So a lot of people say the word LOFUS, and it took me forever to figure out what LOFUS was, but there you go. And it's there to control tip, tilt, focus, astigmatism, and coma. And this is really a great thing. They're going to try to freeze the speckles, basically, so that we can achieve these unprecedented contrast ratios. So there's a couple of options, whether you want to do imaging or spectroscopy. So there's a couple of different masks put in here. And then, of course, we have the IFS. So this is how we do the spectroscopy, which is of particular interest to myself. All right. So, of course, when you put things on a spacecraft, you can't just put them all in a line. So this is basically what the optical bench looks like for the coronagraphic instrument. All right. Next. So here is the WFirst coronagraph performance compared to some of the other instruments that you've heard about during this week. That includes HST. Folks are doing really great work and doing high contrast imaging with HST. Here's JWST, which you just heard about, and of course GPI. With WFirst, which it still says AFTA, we just call it WFirst now, you're going to get these contrast ratios down here indicated by this blue squiggle line here. Okay, so you're getting down to 10 to the negative 10. This assumes post-processing. It includes being able to look at the whole host of planets that we already know about from radial velocity surveys. Okay, so we know they're there. We don't have to go find them. We know that if we point it at the appropriate time, we'll be able to see them. But there's also this big nebulous region of discovery space where we should be able to find things ranging in mass from, say, Earth size all the way up, of course, to Jupiter size object in that particular angular separation range. So I should highlight that this is a technology demonstration. Like I said, this is the first time that we're going to fly one of these in space. So we're going to learn a whole heck of a lot about how to do this. So this is really a great opportunity to really demonstrate that we know what we're doing technologically, especially as we move forward to other missions that may implement similar technologies. It'll have broadband imaging from 430 to 970 nanometers. R of 70 spectroscopy from 600 to 907 nanometers, and it will also have polarimetry capabilities. All right, so I just wanted to highlight some of what we consider the high-level science goals of the WFirst coronagraph, beyond the awesome sort of science goals of these engineering challenges and building this instrument and getting it into space and making it work. We'd like to do some fun things in terms of planets, and that includes detecting planets that span a range of physical properties, and actually include probing populations that are beyond the limits of current surveys. Okay. We're going to use photometry to provide initial discriminators about natures of planets and explore planetary diversity. And then we're going to use spectroscopy to explore the mass metallicity relationship in giant planets and cloud haze formation in giant planets. I want to mention disks because there's a lot of great disk science that can be done with WFirst and will be done with WFirst. And that includes directly image and resolve scattered light from exozodi. So many folks may just think of ZODI as a nuisance parameter, but you can certainly learn a lot from understanding the properties of other solar systems as zodiacal light. Measure those optical properties of disks and ZODI and put constraints on grain properties. We're going to look at spatial disk structure and link it to planet formation, which I'll talk about later, so you can look at gaps in the disk and try to understand what that means. And then also, again, understand the diversity of the system through multi-band photometry. And I've spoke with John Debus a lot about this. This will be the first time that we'll be doing multi-band photometry for these sorts of disk imaging. So this is not done with HST. All right, so planet detection. Step one, is there a planet in my data? So in this case, if we're going to go on a blind search, or we just want to make sure that our radial velocity target is where it should be, we will be using the hybrid Leo mode. And so you'll get images that look something like this. This is contrast ratio and the color scale. And hopefully we'll be able to pick out blobby things that we assume are planets. We'll, of course, have to confirm that either from watching the motion of the planet or, as I'll talk about later, maybe using color diagrams to distinguish it from other potential astrophysical false positives. So in addition to just the raw images, there's going to be a lot of post-processing that's going to need to happen. And these were some figures from Laurent, who gave a talk yesterday morning looking at different techniques. This is the roll differential imaging, angular differential imaging, for noiseless data, so you see these nice blobs, and noisy data. But again, you're still be able to reach sort of these contrast ratios that we expect in the order of 10 to the negative 10. So if you're going to download these slides, I encourage you to go back and look at the talks from yesterday, and I've put the links in here from two experts in the field about techniques and lessons learned from the ground, because these same techniques are the ones that are going to be used for doing the initial planet detection with WFirst. Okay. All right. Hello. Okay. There we go. Okay. Planet characterization. So this is answering the question, what kind of planet is my data? So now you're pretty assured that it's a planet in your data, either from knowing that it's about where the RV target should be, or you have some sense that the thing you just discovered is moving along in an orbit consistent with being bound to the host star. And so here is the sort of yield of planets that we expect with WFirst. So the red ones are the known RV targets, and then we're probably going to discover these blue dots in here that range, of course, from masses around Earth masses through Jupiter masses. They're all going to be clustered in here at about sort of around 1 AU. So we're going to see a lot of things that are near or at the habitable zone of their host stars. And this plot is actually meant to show sort of the populations of things that we've quote-unquote characterized, and that means sort of going beyond just mass or radius. So that includes things where you've been able to get transmission spectroscopy or secondary eclipse information, and then you get a lot of either spectral or photometric information for these directly imaged planets that folks have discussed before. So WFirst is going to add a huge swath of new things where you're going to have either photometric or spectroscopic information to tell you something about those planetary atmospheres. So I mentioned color diagrams, and this is a plot actually by Maggie Turnbull. And what we have plotted here is two of the WFirst bands subtracted from each other. This is our R minus I-ish thing, and another two bands subtracted from each other, B minus V. And what she's done is actually put the solar system planets in this space, so you can see how they sort of separate themselves. You've got Neptune and Uranus down here, Jupiter and Saturn, Titan, Mars, and then Earth, and some of the terrestrial ones in here. And what she also has plotted, however, are the colors of potential background galaxies that might be sources of confusion. So this is the point where if you get something in a certain part of color space, you have to think about, does it necessarily mean that, yes, I have a Jupiter-like object? And then if you're looking at things that could be potentially terrestrial-like, is it potentially a background object? Okay. I want to point out that for WFirst, clouds are great. Everyone bemoans clouds in the land of JWST, but because you're looking at stuff in reflected light, clouds give you almost all of your signal. You don't want cloud-free planets with WFirst. That's a bad thing, okay? The nice thing is that the known radial velocity planets span a range of temperatures, and so this is effective temperature down here, which accounts for both the incoming stellar light, which gives you an equilibrium temperature, and also any potential sort of internal heat flux, versus its mass for the known RV targets. They have a nice span of temperatures that should allow them to have water clouds in a lot of cases, or ammonia, or CH4, methane. They could also have these alkali clouds. And this is interesting because this is starting to overlap a lot with the transiting planet population. So these alkali clouds have been proposed both for GJ1214b and also for HD 189733b. So we may be able to have this region of overlap between transits and direct image targets where you're looking at behaviors of the similar types of clouds. So why do I say that clouds are really, really important? Well, so this is what are called albedo spectra. So here's wavelength in microns, and then albedo. This is actually geometric albedo spectra. So this assumes that you're looking at the planet directly on, and we'll get back to why the exact orbital phase of your planet matters. But I'm comparing a Jupiter-like planet that's at 2 AU from a solar-like star versus a Jupiter-like planet that's at 0.8 AU from a solar-like star. This is work by Carrie Cahoy back in 2010. As you can see, you have this really wampin, sort of nice, strong signal if your planet has a lot of water clouds, and then you can see these columns of methane and water on top of that. If the planet starts to dissipate their water clouds, you start to lose a lot of signal. So the planet will actually be very, very dark down in these wavelengths where we hope to spectroscopically characterize them. Okay. So the other key point here is that super Earths and reflected light are great. So this is work recently by Carolyn Morley for 1214b. We're all pretty familiar with the famous flat line from the HST observations. So this is for the models of 1214 that match the HST data. You can look at the percent change in the transit depth, and you really don't see anything. But if you start looking at the same type of planet in the same temperature range with the same clouds, you'll see a whopping signal in reflected light. So we'll be able to actually probe cloudy super-Earths potentially, probably more likely photometrically. But that's why it's important to learn how to do this from space so that we can start to study these cloudy worlds. So how do we do the spectroscopy? The WFirst CGI spectroscopy mode is slightly different than our search mode. It's going to use this shape pupil it's going to use this shape pupil mask, which gives us this bow tie, as I call it. So you don't want to go searching for things spectroscopically for a number of reasons, one of which it may not be in your bow tie. And then you'll have this lenslet array, you'll get lots of tiny spectra, and then you'll have this data extracted as a function of wavelength. Okay. So your data will end up looking something like this. So this is a realization of a Jupiter-like planet with the WFirst instrument at various signal-to-noise ratios. So most of the signal you're seeing here is really methane, these strong methane absorption features. So here's the underlying model, and then you have the scattering the points you expect at an SNR of 5, SNR of 10, or SNR of 20. And to achieve these various SNRs will take varying lengths of integration time. Okay, so just to give you an idea of what WFirst spectra might look like, it looks pretty reasonable to me, actually. But And we've already started to do spectroscopic retrieval exercises, but it's taken a lot of revamping the models that we typically use for transits, because again, this is a reflected light signal. So this isn't the same as transmission, where you're looking for absorption as you pass through the limbs of your atmosphere, or even secondary eclipse thermal emission observations. You have to take into account all the scattering properties of your cloud deck that's underlying the column of gas that you're probing. So we've used a sort of a simplified model of the atmosphere, and this is something that's been done in the solar system community for Jupiter. And we look at constraining things such as the albedo and scattering properties of the cloud, its optical depth, and also looking at the surface gravity of the planet, and then also different types of clouds and hazes. And most importantly, we really want to get a good constraint on the methane abundance, because we can use the methane abundance to make an estimate of the planet's atmospheric metallicity. And in doing that, we can then test the mass metallicity relationship that you've heard mentioned a couple times this week. And this paper right here just came out recently. If you want to learn about retrieval in reflected light, I recommend that you go get it. It's a nice sort of 30-page behemoth document. All right. So I want to highlight that orbital phase matters. Everything that I showed you before assumed that you somehow magically got the planet at sort of 90 degrees, or at 0 degrees phase, so based on what we call the geometric albedo. You will never, ever have that scenario. More likely, you're going to be looking at a planet closer to quadrature. So what happens as a function of orbital phase is that you go from a spectrum that looks something like this, so this is 0 degrees, so this is the geometric albedo. These very nice, strong, deep signals. And as the planet goes around at these different phase angles, you'll see that these features get shallower and you start losing more and more signal till you're down here at 120 degrees and basically the planet goes dark. So 90 degrees or quadrature is where we're probably going to see a lot of these planets. So we have to make sure that we understand what the spectroscopic signature should be at these various phase angles and the possible degeneracies there are between things like phase angle and the radius of the planet. Okay, so there's work being done on that now. Orbital phase also matters in the sense of photometry and making color diagrams. So I showed you that nice color diagram before that hopefully would let you tell a background galaxy from an Earth-like planet. Over here I have just basic V minus R and R minus I plot for the planets in our solar system and their geometric albedos, and they're nicely segregated from each other. And you could say, oh, I could definitely tell Neptune apart from Uranus, or certainly apart from Jupiter in this phase space. But if you start to consider how those colors vary as a function of orbital phase, it becomes a gigantic sort of mess. So this is something that needs to be considered when thinking about even spectroscopically or using color diagrams, how you might expect things to vary as a function of orbital phase. All right, so let me briefly touch on disk detection and characterization. Here we have a simulation of the system 47 UMA with a 30 Zodi disk. So you definitely detect the disks and the planets embedded in here. So this is a lot of, 30 times what we have in the solar system. And then here's our sort of bend SNR map. So for systems like 47 UMA, we should be able to get really great information about both the Zodi, potentially planets buried within there. We also want to look at systems where we might be able to see sort of clearings in the disk. So you can see these blobs here, which are planets, and they're actually clearing gaps in the disk here. And what we've done is we've taken this original scene and then convolved it with our version of the instrument simulator, and it comes out looking something like this. So not quite as pristine, but you still gain a lot of information, especially at this brightening right here. And doing that at multiple bands will allow you to better understand the scattering properties of the disks and also potentially understanding if these band clearings are significant. All right. So I briefly want to mention, and Carl already brought this up, that we are now considering what it means for WFirst to be quote-unquote Starshade ready. So we are considering how we can make sure that the current design is able to accept a Starshade that may show up at a later point in time. How much time do I have right now? Okay. So I'll just start this little movie. I'm sure most of you are familiar with the Starshade at this point. Or I should ask, how many people, whoops, back, not working. Yeah. So who here is, there it goes, okay. So the beauty of the Starshade is that it would allow us to get a lot more spectroscopy for planets, and potentially spectroscopy for planets that are sort of smaller than Jupiter size. And for me, that's a very valuable prospect to be able to do that. So in this case, instead of them launching together, you would already have WFirst out at L2, and then you would launch a Starshade out to rendezvous with it. And then you would use that to do potentially follow-up of targets that were discovered using the internal coronagraph during the first few years of operation. Okay, so there's your little planets behind the giant sunflower of doom. So, all right. So opportunities for you. I've already mentioned the guest observer program, so I think it's important that you keep that in mind, both for the wide field instrument and also the coronagraph. Maggie Turnbull, who is one of the leads of one of the science investigation teams, is running a number of data challenges. Okay, so this is your chance to try to do WFirst coronagraph science now. And the first one is actually going to be a spectroscopic retrieval exercise. So doing some of the similar work that we've done recently, trying to determine the methane abundance for RV targets that are going to be looked at with WFirst. That's for this year. The plan is there to be a new data challenge in each subsequent year, which will include extracting planets from data cubes. So it should test everybody's skills, from the theoreticians to those that are maybe a little bit more familiar with instrumentation. So the first data challenge is next month. And if you're interested, you can go through the slides and email Maggie. There'll be telecons next week. And this is sort of the scheme of what she's trying to do with this first data challenge. Okay. So I wanted to highlight the online resources. There's lots of them, but in particular, I wanted to show you the information at the IPAC website. As it's loading. All right. So this is the go-to place if you want to understand the current capabilities of the coronagraph. It has all of the throughputs, etc., where the band passes are down here. So all of this is kept up to date. So if you want to take your theoretical model and figure out what it would look like, potentially with WFirst, you can come here. Or just to get a better understanding of what the capabilities are for a particular science case that you're thinking about. They also have some forward models. I think it's this one. No, where'd it go? I think it's under, is it simulation code? Maybe. Yeah, hold on. So there's a place in here that has models, and I just lost it. All right, let's try this one. There you go. Well, so there's lots of models in here for the instrument. I don't know where there is also a library of albedo spectra somewhere in here. So if you haven't made your own albedo spectra, you can go here and grab them. We're trying to keep adding to that so that folks can make their own scenes, etc. All right, and back to the talk. Keynote. Forward. And that is basically it. So hopefully, at least you have a better sense of what the coronagraphic instrument on WFirst is trying to do. Of course, we haven't finalized the design. We're still in the process of setting requirements, etc. But I think it's going to be a really important tool moving forward in our quest to detect life on other worlds. I mean, this is how we're going to learn how to use a coronagraph in space. We're going to make some awesome measurements of Jupiter, potentially down to super Earth-sized planets, and really start to understand planets that are at and near the habitable zones of their suns. So, taking questions. So the question was, what does Starshade Ready actually entail? We're currently investigating what that actually means. So there's a large group of people who are part of the Formulation Science Working Group, and there are different levels of sort of Starshade readiness, from basically like, okay, it has a beacon, and then that way it can communicate, to, starting to think about altering the design of the coronagraph itself to potentially enhance the Starshade science. So the polarimetric capabilities, in some sense, come for free because of the wavefront sensing. But you'll be able to, in the broadband when you do the broadband imaging, not with the spectroscopy, with the broadband imaging, you'll be able to get basically two polarizations. So you can use that then to figure out the Stokes parameters. That makes sense? Okay.
What kind of exposure times are you looking at in order to get down to 10%?
So it matters it matters. Oh, sorry. The question was, what sort of exposure times are you looking at to get down to 10 to the negative 10? It matters what you're trying to do, first of all, if you're trying to do detection or spectroscopy, but something on the order of days to weeks is in the right ballpark. Yes, so it has the question was, yes. With WFirst at L2, is it still serviceable? And the answer is yes, it is designed to be serviceable robotically. Or if we suddenly send people, to L2. So you're always probing the column of whatever's above your cloud deck. Now, you can't form a thick cloud high up in the atmosphere, you just run out of material. So there will always be something above the cloud deck to detect. But yes, you will get a range of depths, depending on how deep in the atmosphere your cloud is, you'll get a range of depths of atmospheric features.
So do you think by measuring the albedo of giant planets, you can put constraints on the composition?
So yes, because the question was, do you think by measuring the albedo of giant planets we can put constraints on the composition? So by measuring the albedos spectroscopically, so as a function of wavelength, yes, because you have those very, very strong methane features, potentially other molecular features. We might be able to get some weak water, we'll see. But in the same way that we've determined metallicity for solar system objects, we can do the exact same sort of calculations for these WFirst targets.
How much will the patchiness of the cloud cover affect the results? So do you want to assume kind of constant cloud?
The question was, how much will patchy clouds affect your results? Of course, we won't be able to resolve the clouds. The models that we use for generating albedo spectral and doing the retrievals have this ability to have patchy clouds in them, so we can investigate the effect of cloud patchiness. And there's actually a student, I don't know if Matt's here, working on that right now. We have seen from observations of Jupiter by Cassini, we were able to get a phase, basically look at the phase curve. So they track the albedo as a function of orbital phase for Jupiter and compare them to our own model predictions. And there's a slight discrepancy that can be largely explained by patchiness of clouds and banding. If we had all Rayleigh scattering, it would be more like this Jupiter at point 8 AU, wherever it went. So the Rayleigh scattering, of course, is very strong in the blue. Okay, so your Rayleigh scattering will dominate when your atmosphere is relatively clear and just dominated by atoms and molecules. So, but remember, for WFirst, we have a couple bands out here, which is great. These bands out here are also going to allow us to study the effects of hazes, so small particle scatterers. But if you were trying to get a spectrum of this thing from, say, 0.6 to 0.9 microns, you wouldn't see anything.
Okay.